Okie dokie. So today we're going to start off learning with the ozone, and we're going to end on greenhouse gas concentration. So we're going to be going through it. So before we even start, we're just going to go over basic atmosphere. So the lowest part of the atmosphere, which is from here to here, is called the troposphere. And then from about 15 kilometers to about here, that is stratosphere, then thermosphere, mesosphere, and then finally thermosphere.
Okay.
So, within the atmosphere...
Is this it over here, thermosphere?
Yeah,
what is
there it is.
That
is the mesopause, which is between the mesosphere and thermosphere.
Okay, and then this is...
And that's the stratosphere, which is above the troposphere. So the troposphere is what we're in right now.
Yeah, that's
It's
what
from
we
the
got.
surface up to like about 15 kilometers.
Okay.
So, right about right here is the ozone layer. And so it's from about 15 kilometers to about 30 kilometers. Now, it's not actually that thick, but depending on where you are in Earth, depends on how high up it is, it's about this thick. The ozone layer is about this thick.
Yeah.
And it's not very thick. It's about maybe 3 or 4 inches, maybe. Not even. So, within the atmosphere, we have a pretty even chemical makeup. We have nitrogen, 80% of the atmosphere is nitrogen, a little less than 20% is oxygen, and then you have all those other fun chemicals. I think 0.004% is ozone. There's other fun things, waters in the air, all that good stuff. So, the question becomes UV radiation. How does UV radiation work? So you guys are familiar with UVC, UVB, and UVA, correct? You know the UVs?
UV, yeah.
Ultraviolet?
Ultraviolet lights.
We can't see them with the naked eye. If you look at this part of the graph, this is stuff you can't see, visible, and then infrared, so this is heat. Infrared. I always say infrared. It's what happens when you learn how to say a word reading and not hearing. And so when you look at waves like these, waves like UVC, they're tight. They're tightly coiled. And then UVB is a little more loose, and then UVA is a little more loose, and then visible is much looser, and then infrared is even looser. And so UVC, and this is the weird thing about how they measure waves, is that the smaller the number, the tighter the wave, and then the bigger the number, the looser the wave, and nanometers. And so, when we're looking at the atmosphere, UVs are actually slowed down, and actually never even, most 97 to 90% of UVs never reach the surface. And that's because, well, they're stuck in the atmosphere. So if you look at UVC, which is the tightest coil, at about somewhere in the thermosphere or mesosphere, it's going to hit nitrogen. Now, what do I mean by it's going to hit nitrogen? This is where chemistry gets involved. So you see nitrogen right here, and it has that really strong bond, those 3 bonds right there.
Yep.
That's not going to be easy to break. That's going to be hard to break. Then you see oxygen. Oxygen has those 2 bonds right there. Not easy to break, but more breakable than nitrogen. And then you look at oxygen. Ozone. And ozone, of course, has a very strong between 2 oxygen. It has the 2 bonds. But then the 3rd oxygen, you'll see it has that weak 1 bond. Why is this important? Well, let's go back to our picture here. So, the tightly coiled UVC is strong, and it can break nitrogen. Now, UVB and UVA, they're too weak. They won't break nitrogen bonds, but UVC will. And as UVC comes into the atmosphere, it's going to break up all these nitrogen bonds, and UVC actually won't even make it anywhere near the surface. And so we go to UVB. UVB is stronger than UVA, weaker than UVB. UVB break up oxygen. This becomes very important later in the creation of ozone. So UVB comes down to about 40 kilometers, and it's going to break up oxygen into two separate oxygen atoms. And now we look at UVA, the weakest of the bunch. It can't break up nitrogen, it can't break up oxygen. It can, however, break up ozone. And where does it break up the ozone, you ask? Yes, that weak little bond right there.
Yep.
And so, as you see that right here, 126 nanometers, in other words, UVC breaks up nitrogen, about 250 nanometers, that will break up oxygen, that's UVB. And then UVA, 310 nanometers, that's going to break up. That's going to break up ozone.
Yep.
So, how is ozone formed in the ozone layer? That's actually really fun. So, we have a bunch of, just oxygen kicking it in the air, right? And then, of course, you remember how O3 is broken apart by UVA, right? Well, that means we have a bunch of just free-flying oxygen in the air. And so what does it do? It matches up with an O2 and makes O3. Conversely, we have O3 getting hit by UVA, making O2 and planet O. And so that is how
it goes around.
Right. So, have you kids ever heard of the ozone hole?
No, we haven't. Tell us about the ozone hole.
All right, the ozone hole is over the Antarctic, and that's actually really interesting. So you know the Antarctic, how it has only one day and one night? They last for 6 months each. Well, in the night, I should actually back up here. Let's back up. Refrigerators. Do you remember when they came out and became really big? Like actual refrigerators, not ice boxes. Yeah. Right. And so they came out with this funky chemical, CFCs. So carbon, fluoride, and chloride. Yeah. They're great. They're great for refrigeration, aerosol. They're cheap and easy to make. They're virtually non-toxic to humans in short term. And so we used these in the 50s, the 60s, the 70s, and then the 80s came around, and scientists looked up at the ozone and went, oh crap. They realized, uh-oh, chloride is a bit of a problem. The chloride and CFCs. And so why is it a problem? Well, it's a problem because it gets into the stratosphere and into the ozone layer. And so what happens is, well, really, it truly is the perfect storm. And so you look down to the Antarctica, and of course, it's night. And during the night, it becomes freezing, wind patterns stabilize, and a polar vortex forms. So pretty much air is just circling around in the Arctic. And then you got these fun polar stratospheric clouds forming. And these clouds, of course, have, well, they're made of actually, what is that lovely stuff called? They're made of acid, I'm pretty sure. Let's see. I have it written down somewhere. Hydraulic acid, if I remember correctly. No, nitric acid, excuse me. They're nitric acid clouds. Anyway, the fun thing about surfaces accelerate reactions. And so this is important because you have all those CFCs in the air and all those clouds in the air, and then you have that all collecting during the night, and then day rises. And so what comes with day? Sun. And what comes with sun? Heat. Heat. But also the UVs. And so you have UVs coming down, and UVB hits the CFC molecules and it breaks the bond holding on that chlorine. Now, why does that become a problem, you ask? Well, I'm happy you asked. The chlorine grabs onto our friend ozone.
Yep.
And so chlorine grabs on. Cl equals O2 plus OCl. Now, what's the biggest problem about this? Well, chlorine can detach itself from the O and reattach itself to more ozone. And so you have rapid depletion in the Arctic of ozone. There's hundreds of millions of these things out there.
Mm-hmm.
And so from I want to say, no, it's July to November. It's their springtime. August to November? No, September to November? Anyway, their springtime, Arctic springtime, it's a nightmare out there. 60% depletion of the ozone layer, which causes serious problems, as you can imagine, because we're relying on the ozone layer not only to keep the UVs out, but also to keep heat in.
Yep.
So that moves us on to the second part of our presentation. Oh, wait. You may be asking, CFCs, do we use them anymore? No. The Montreal Protocol in 1988 is one of the very few pieces of legislation that 146 countries agreed on.
Right.
We all went, no more CFCs, and so we made fun things. We have hydrofluorocarbons now.
Okay.
HFCs. They don't have any chlorine attached to them, and so that's what we use in refrigeration. They're all the rage with the kids these days.
All the rage with the kids.
Yeah, that's what we're using today. So before I go on, are there any questions?
Yeah, why are the kids interested in the CFCs?
Well, CFCs break down the ozone, so we don't want that.
No.
HFCs don't break up the ozone, but they cause other problems.
Right.
Well, I'm glad you asked. They cause issues because they're greenhouse gases. And so do you guys know what greenhouse gases are?
You better tell us.
So greenhouse gases can be broken up by UVs, but when they're hit with infrared radiation, they don't absorb, they start to stretch. And so there are pretty much 3 different ways that greenhouse gases can move. They can kind of do like an up and down stretch. They can go an in and out stretch, and they can do both. They look like Zumba. That's very true. And so we have a bunch of them. Greenhouse gases include water vapor. They include CO2, methane, NO2, HFCs, which I mentioned already, and CFCs are greenhouse gases too. And so as these are bending and stretching, what happens is they're creating heat. So they're heating up the atmosphere. And even worse is what happens is they take in infrared radiation and then they spit it back out in all directions. So some of it does go off into space, which is just great, but some of it comes back down to the surface.
Right.
Yes. And so this is what's causing global warming.
Okay.
Which is not ideal.
No.
Yeah.
So, we've named greenhouse gases lots of fun, and so as I was talking about earlier, we want ozone, because if we didn't have ozone, and if we didn't have any greenhouse gases, we would be like Mars. Actually, no, we would be like the moon, where when the sun's beating down, it is super duper hot, and when there's no sun, it's super duper cold.
Yeah.
And so that's one of the reasons why there isn't life on Mars, is because they didn't have much of an atmosphere. They can hold on to their water. And then plus, you know, all that radiation would come down and kill anything, or at least any, yeah, exactly.
So we're very lucky that we have the ozone layer because it keeps heat in, but also keeps UV out.
Yeah.
Now the issue with having too much greenhouse gases inside of our atmosphere, of course, is that temperature is slowly going up. One of the biggest issues is the CO2 concentration. We have an unnatural amount of CO2 in the air, and actually if you look at if I were to show you a graph of CO2 concentration in the last few years, let's just say this is the concentration,
Yep.
and this is maybe 1800s. Let's say this is 1900s. Let's go ahead and say that this is the 70s, and this is now. We're looking at something that's like, looks like that. We're looking at something that looks very much like that. No, it goes up. We don't even know when it'll cap.
Good if it's the market.
If it was the market, it would be good news.
Yeah.
Now, actually, here's the funny thing. If, like, let's say we just looked at this small part right here of CO2 concentration as it goes up, we're going to see that it does this.
Yeah,
So it goes up and down and up and down. But there's a reason why it does this. And it follows the growing season. Because, as you know, plants take in CO2.
Mm-hmm.
Exactly, and that's oxygen. Conversely, when plants die, what happens?
It all
They
goes.
release CO2. So, would planting more trees solve our problems? No. Would it slightly help? Yes.
Yeah.
So, let's see here.
Step in the right direction, but futile.
No, yeah, it would be problematic. And I've already covered why greenhouse gases concentration will lead to a warmer Earth on average, and that would be because they would be spitting out more. So, we've gone all over the fun stuff. Do we have any questions?
How do we fix it?
How do we fix it? Well, we would need to be radical and we would need to be fast.
Huh?
A lot of it,
Very fast.
radical and very fast. We would have to target a lot of the big companies, coal burning, all of that stuff. We would need to find clean energy. One of the easy things for us to do is to try using the car list or public transport. Trying to get your power from not coal plants would be good. That's really hard to do. I know in Tucson we get about 20% of our power from
Wind.
solar, which helps a little. Of course, recycling, trying not to, buy too much plastic, all of that stuff. I mean, it adds up, but quite frankly, its legislation is going to be what helps the most. Definitely tighter EPA rules. So that would be, how do we fix it? Is there any more questions about anything else? Chemicals, anything? No. No?
None that I can think of.
None that you can think of?
But, I think that I thought we were going to talk about the problem, how to solve it.
I'm just supposed to teach you what's going on.
Yeah.
How do we solve it? I mean,
Well, how do you prove it?
how do you prove it?
It's going on.
Well,
it's a nice explanation.
What they're doing, it's actually really cool. So they have a lab in, well, they have labs everywhere where they will measure chemicals in the air. Of course, they have the big lab in Antarctica. They, of course, are measuring the atmosphere and how much UVs are coming down and how much ozone is really up there. You can actually see some really startling maps of how much it truly does thin out during the year.
Okay.
Of course, and then everywhere across the world, they're constantly measuring air, what's in it, in the atmosphere and stuff like that. So you can actually go online and look up Naples, Florida, and you can see air quality. The air quality index that also helps prove that, you know, we have more carbon, CO2 in the air, and we have more emissions in the air that shouldn't be in the air. So, is that all good?
Yeah.